Welcome to the Beanium lab procedure. Introduction. Dalton's atomic theory states that all atoms of a given element are exactly identical. However, this is not entirely true. Scientists are aware of the existence of isotopes, which are atoms of the same element that have a different number of neutrons. Since the number of neutrons differs, the mass of each isotope is also different, but the atomic numbers are identical. For example, carbon-12, carbon-13, and carbon-14. Isotopes of an element behave the same way chemically. The only differences are the number of neutrons and the mass. So for example, carbon-12 has 6 protons, so does carbon-13, carbon-14. They all have 6 protons. However, carbon-12, 12 minus 6, carbon-12 has 6 neutrons. Carbon-13, 13 minus 6, carbon-13 has 7 neutrons. And carbon-14, 14 minus 6, is 8 neutrons. Look at the atomic masses on your periodic table. You should notice that they are not whole numbers. This is because elements in nature are found as a mixture of isotopes with different masses. Scientists calculate the atomic mass of an element by taking into account the relative percentages of each isotope in nature and multiplying it by each isotope's mass. This is called a weighted average and is in the same way your grades are calculated in your chemistry class. Tests are counted more than labs. Purpose: to determine how the average atomic mass of an element is calculated. We will need a Beanium sample, an electronic balance, we'll use some weigh boats, and a calculator, and you should have a periodic table. Procedure: obtain a Beanium sample and completely clean your lab desk of all clutter. Remember, Beanium is fictional. Each type of bean represents a different isotope. Sort the beans into 3 groups based on their type. Give each type of bean a description recorded in the data table. Count the number of atoms of each isotope/bean recorded in the data table. Add up each type of bean to get a total number of isotopes/beans recorded in the data table. Calculate the relative abundance of each isotope, part over whole times 100, recorded in the data table. Select one type of isotope and mass all of the atoms of that isotope together, recorded in the data table. And finally, repeat step 7 for the other 2 types of isotopes recorded in the data table. So our first step is we take the beans and we're going to sort that into 3 categories. So we have a large, round kidney bean, ovular, oval kidney bean. We have a white lentil bean. And we have a medium brown speckled bean. So we'll sort them. Now that they're all sorted, we'll categorize them. Color and size we'll do for the first one, large, maroon. For the second one, we will do medium, brown. And for the third, we'll do small and white. Step 4, count the number of atoms of each isotope beam. So we got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91. So you have 91 small white beans. For the large maroon, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62, 64, 66, 68, 70, 72, 74, 75. 75 large maroon. And finally, medium brown, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 61. 61. So total number of beans, 75 plus 61 plus 91. That gives us total 227 total beans. So relative abundance, we're going to do part over whole times 100. So we'll do 75, right over here, 75 divided by 227 times 100. This one will be 61 over 227 times 100. And this one will be 91 over 227 times 100. So for the first one, 75 divided by 227 times 100. That'll give us 33.04%. 61 divided by 227 times 100 gives us 26.87%. And finally, we have 91 divided by 227 times 100, which gives us 40.88%. Excuse me, 40.09%. 40.09%. Finally, we have to take the isotope mass. For the isotope mass, we take each of one type of beam and measure the mass on the electronic balance. So we'll turn the balance on. Let's take a weigh boat and make life a little bit easier. Zero it out. We can start with the large beam. Try not to lose any of the beans in the process. That'll affect your results. $37.36 grams. Then we'll do medium brown. Take another weight boat, zero it out. Once again, try not to lose the beans. We have 19.47 grams. And last but not least, small white. Take a third, weight boat, zero it out. These are very small, be careful with them to not lose them. And finally we have 15.19, excuse me, yeah, 15.2, we're still bouncing around a bit. 15.21 grams. So our large maroon beans, there were 75 of them. Relative abundance, 75 divided by 227 times 100, that worked out to be 33.04%, and the mass was 37.36 grams. Our medium brown beans, there were 61 of them. And part over whole, 61 divided by 227 times 100 works out to be 26.87% and 19.47 grams. And finally, our small white beans, we had the most of those, 91. 91 divided by 227 times 100 works out to be 40.09%, and the mass is 15.21 grams. The total, as we said, is 227 beans, and we completed all 8 steps. Next, we will perform some calculations. Question 1. For each type of bean, calculate the average mass of that isotope. Take the mass of all the same isotope beans and divide it by the number of beans of that type. So step 7 from page 1 divided by step 4, number of beans. So we have from step 7, for the first bean, that is the large maroon bean, that'll be 37.36 grams, divided by number of beans, we had 75 beans. So we do those, 37.36 divided by 75. So we have 0.4981 grams per bean. Bean 2, that's the medium brown, we had 19.47 grams, divided by total number of beans was 61 beans. $19.47 divided by 61, and we get 0.319 grams per bean. And finally, last but not least, number 3, we have 15.21 grams divided by 91 beans. 15.21 divided by 91. and we get 0.1671 grams per bean. Let's do 0.3192. So we'll keep it all even. Step 2, calculate the average atomic mass for beanium. So, average mass of bean 1 times abundance of bean 1. So we have 0.4981 grams per bean times the abundance of bean 1 we calculated to be 33.04%. So 0.4981 times 33.04, and that gives us, with 2 decimal places, 16.46 grams. Bean 2, we have 0.3192 grams per bean times 26.87%, 0.3192 times 26.87. We get 8.58 grams. And finally, bean number 3, we have 0.1671 grams per bean times the percentage, which is 40.09%. So 0.1671 times 40.09, and that gives us 6.70 grams. Add them together, 16.46 plus 8.58 plus 6.70. That gives us a grand total of 31.74 grams. And if we divide that by 100, we get 0.317 grams. So once again, our answers for bean 1, 0.4981 grams per bean. Bean 2, 0.3192 grams per bean. Bean 3, 0.1671 grams per bean. Step 2, calculation number 2, bean 1, 16.46 grams, plus bean 2, 8.58 grams, plus bean 3, 6.70 grams. When you add those together, you get 31.74 grams. Divide by 100, 0.3174 grams. Thank you for joining us during this Beanium laboratory procedure. I hope you learned something today. Please join us again soon.